Welcome to qnawire.
So we have a spaceship that's orbiting above a planet that has a radius rp, and then the ship is an additional height h above the surface of the planet, moving with velocity v. And so we're given all of these values, of the radius, the height, and the velocity here. So then we want to know if we land on the planet and launch a projectile with initial velocity v naught at an angle theta, and again we're given those values, what distance d will it travel horizontally? So what will its range be? So just from a kinematic standpoint, this looks like a great application of the range equation, which tells us when we're on flat grounds like this, so there's no change in the initial height, and we just launch something with some velocity v at angle theta, that range will be that initial velocity squared over the gravitational acceleration, so usually Earth's, but in this case on a different planet, what that value of g will be, and then times sine of 2 times the launch angle, so 2 theta. So this is a nice result to have on hand, but if you didn't know this, all we would do is just kind of the classic way of doing this problem. So we could break this initial velocity into x and y components, and then we'd look at the y component to see how long the projectile would be in the air for. And then we would look at the x components and say if it's traveling horizontally at some speed for that amount of time, how far will it have gone? So looking at this equation, though, all we need is to find what g on this planet is, and then we should be able to evaluate this. So the way we want to do that is we can find the mass of the planet from this orbital information of the spaceship they tell us. And once we have the mass, we can just calculate what g will be. So we know that the velocity for circular orbit is the square root of g times the mass of the planet times r, or divided by r. So r here, the total radius, so from the center of the planet all the way out to the spaceship's orbit. So we can solve for MP here, so just squaring both sides and then moving these terms, we get that MP is equal to v squared times r over g. And then r here, remember, is just the radius of the planet plus h. So we have both of those terms, and then divided by g. And so we find then that that is 1.84 times 10 to the 24th kilograms. And so now that we have that, we can just say that g will be the gravitational constant times the mass of the planet divided by the radius of the planet squared. So we again have all those values now that we found the mass, and so we get that that's going to be 6.11 meters per second squared. And so now we can apply that to this equation. And so we say our range, our horizontal range d, will be v naught squared. So they tell us to take v naught as 12.6 meters per second. So that's squared, divided by our value of g, 6.11 meters per second squared, and then times sine of 2 times a theta of 30.8 degrees. And so we do that, and we should get that the range is 22.8 meters.